Let's start off with a new chapter today on magnetic field. Permanent magnets, current carrying conductors, or moving charge produce a magnetic field, also known as a B field, in the region around them. A magnetic field is a region where a magnetic force is experienced by a magnet, a current carrying conductor, or a moving charge. Now, it's important to note that any moving charge will produce a magnetic field. For example, if you're talking about a current carrying conductor, there is a flow of charges, thus a magnetic field is produced. Let's imagine this right now. If this is your wire, and we say that you have current flow in this particular direction, that current flow actually consists of a flow of charges in that direction. So let's just say maybe we have electrons here that make up our current. All these electrons are going in this general direction, so the charges are moving, you therefore have a magnetic field produced. As for magnetic materials, the electrons orbiting around a nucleus or a spinning nucleus itself also produces a magnetic field since the charges are moving. Let's just say right now you have a particular atom. This one is your nucleus. And then around your nucleus, you have electrons orbiting around it. So in your case, your electron is moving. Your nucleus, in some cases, is also spinning. So regardless of whether you're looking at the electron or the nucleus, they are moving here. So you must have a magnetic field produced. When it comes to magnetic forces, the forces will be repulsive when like poles such as north and north or south and south are close to each other, and they would be attractive when unlike poles such as north and south are close to each other. Just like electric field, field lines can also be drawn to represent a magnetic field with the following characteristics. Direction of your magnetic field follows the direction of force acting on an isolated north pole or end pole of a magnet placed at a point in the field. As such, your field lines will always tend to come up from the North Pole and into the South Pole. And then next one will be that the strength of your field is determined by the spacing of your field lines. The closer the lines are to each other, the stronger your field and vice versa. Whereas if you have equal line spacing, this indicates uniform field strength or constant field strength. And lastly, the field lines are always continuous and never cross each other. The diagram below shows you some examples of magnetic fields. You have a bar magnet for the first diagram, you have a horseshoe magnet for the second diagram, and you have two bar magnets for the third diagram. For your syllabus, you really only need to remember the first one. You need to remember what are the characteristics of the field and how to draw it, okay? Now, as mentioned to you earlier, the spacing between your field lines is a measure of your field strength. Where the closer the lines are to each other, the stronger your field. Another way to think about it is in terms of the relative density of your field lines. That would also be a measure of your field strength. Because the higher the density of your field lines per unit area, the stronger the field, since the lines must be packed closer together here. So to illustrate this, let's just consider two areas that are of the same value. For the first area on the left, you have maybe only two magnetic field lines passing through it. But for the second area on the right, you have a lot more field lines passing through, like this. So if you compare between the first area and the second area, for the second area where you have a higher density of field lines, you have a higher number of lines passing through per unit area, the lines must be packed closer together in order to fit that same area. So as a result of you packing them closer together inside that same area, it thus follows that the spacing between your field lines must be smaller. So your field strength would be higher now. So usually when you're talking about magnetic field strength, we also commonly call it magnetic flux density B. That will be the term that we normally use in this chapter. As part of your syllabus, you are required to know how to draw the magnetic field for certain select cases. The first case being that of a straight current carrying conductor. Earlier, we mentioned that current is a flow of charged particles. The charges are moving, so you will have a magnetic field that is produced around any conductor or wire which carries an electrical current. So we know a magnetic field is produced, but how would the magnetic field look like? If you were to consider a wire like this right now, where you have a current flowing in this direction, the magnetic field that is produced will be in the form of concentric circles. Okay, so the first thing to note is that you would have few lines forming a pattern of concentric circles around the wire. And because magnetic field has a direction associated with it, how would you predict the direction of your magnetic field? To predict the direction of your magnetic field, you will need to use something called the right-hand grip rule. So to use the right-hand grip rule, what you will need to do is that you imagine the wire being gripped with your right hand such that the thumb points in the direction of the current and the fingers are actually pointing in the direction of the magnetic field. So if you look at the second diagram below here, you have a wire and then you have a current pointing outwards. You imagine right now that you use your right hand to grip the wire. Your thumb should be pointing along the direction of the current, whereas the curl of your fingers will be giving you the direction of your magnetic field. So in this case, it should be pointing in the counterclockwise direction. That is how you predict the direction of your magnetic field. Now, a lot of times you won't be required to draw your magnetic field pattern in 3D like this. Instead, you will be required to draw them in 2D, like the ones that you're seeing below here. So to draw them in 2D, usually you try to visualize them by looking at the magnetic field from above. Now, when viewed from above, if the current is coming towards you or is coming out of the plane of the page, the current is represented with a dot like this. And on the other hand, if the current is going away from you or moving into the plane of the page, the current is represented with a cross like this. Okay. After drawing the current, all that's left is to draw the pattern of concentric circles. Now, when you draw the pattern of concentric circles, you need to be mindful about the spacing of your field lines, since it is a measure of your field strength. So for a current carrying conductor, the spacing between your field lines increase with distance from the wire. The reason being that the field is stronger near the current and weaker further away from the current. So what this means is that if you're going away from the center of the wire, the spacing of your field lines must be drawn in such a way that it increases. Because the idea here is that if your distance increases, your magnetic field strength or your magnetic flux density must be decreasing. So therefore, spacing between lines must increase. When it comes to your field strength or flux density, if you want to change its value, all you just need to do is to change the current. In general, your field strength or flux density increases when your current is increased. And when you reverse the direction of your current, the direction of your magnetic field reverses too, which can still be predicted using your right-hand grip rule. If you look at the remaining diagrams below, specifically for this first pair of wires, the current direction is opposite to each other. The wire on the left is having current direction upwards, whereas the wire on the right is having current direction downwards. They will still produce a magnetic field around the wire, but for the wire on the left, the magnetic field would be counterclockwise, whereas the wire on the right would have a magnetic field clockwise. You can still predict the direction using right-hand grip rule for each of them. And then you look at the second pair of wire below here, the current direction is the same, but the wire on the left is having lower current, while the wire on the right is having a larger current. The one with the lower current will produce a weaker field, whereas the one with the stronger current will produce a stronger field. You can actually see this from the line spacing. The one with the weaker field has larger line spacing, whereas the one with the stronger field has smaller line spacing. Now, the next case we want to look at is that of a solenoid. Earlier, we mentioned that a current carrying wire produces its own magnetic field. If we want to concentrate the magnetic field produced by the wire, what we can do is that we can wind the wire together into something called a solenoid. A solenoid is just a coil of insulated wire with many turns, just like that of a spring, such that when current flows through it, you have a magnetic field that is formed that is similar to that of a bar magnet. If you look at the diagram below, the first diagram on the left is that of a solenoid. The magnetic field that is formed around it is very similar to that of a bar magnet. Now, inside your exam questions, when you want to draw it out, you would normally draw it as the diagram on the right, where you imagine yourself as cutting the solenoid in half and you draw what you see along the cutting plane. Okay, now for the magnetic field that you draw, then there are a few things to note. The first one being that inside the solenoid, the magnetic field is uniform, so the lines must be drawn as equally spaced parallel lines. In the diagram above, you can see them being drawn with equal line spacing. This tells you that you have uniform flux density. How about the case outside the solenoid? Outside the solenoid, the field is weaker and diverges coming out from the ends, which is drawn as lines with varying spacing. So over here, when you draw out the field lines, make sure that the line spacing is increasing. Okay? When your line spacing is increasing, it tells you that your flux density is decreasing. Okay? So let me just write it over at the other end too. And the next thing to note is that along the cutting plane, you will notice a series of dots as well as a series of crosses. The dots here represent the current direction out of the plane of the page, while the crosses represent the current direction into the plane of the page. And when you draw out your magnetic field, remember that magnetic field tends to have a certain direction to it. The field lines normally emerge from the North Pole and return to the South Pole. So how do you determine the direction of your magnetic field in the first place? The direction of your magnetic field can be determined using the right-hand grip rule as before, but this time there are some modifications to it, where your thumb is now the direction of magnetic field and the curl of your finger is the direction of your current. It has been switched around. Now imagine gripping the solenoid using your right hand. The fingers represent the direction of current flow in the solenoid, while the thumb points in the direction of the magnetic field inside the coil. It is actually now pointing towards the end of the coil that behaves like a North Pole. Now, if you apply this rule to the example above, using your right hand, the curl of your finger represents the direction of your current, whereas the thumb represents the direction of your magnetic field. It is pointing towards the end of the coil that behaves as a North Pole. This other end here must be your South Pole then. As the solenoid behaves like a magnet only when current flows through the coils, it is thus known as an electromagnet. Now, when you want to increase the strength of the magnetic field of a solenoid, there are a number of things that you could do. The first one is to place a soft iron core or any ferromagnetic material inside the coil. And then the second thing you could do is to increase the current flowing through the coil. And lastly, you could also increase the number of turns of the coils. For the last 2 points, they are actually summarized by this equation here, where you say that B is equals to mu naught and I. B is your flux density, N is your number of coil turns, I is your current. Now you will notice that there's a particular symbol you have never seen before, mu naught. That symbol is actually representing the permeability of free space. What is permeability of free space in the first place? It measures how easy it is for a magnetic field to pass through vacuum. The value of mu naught is actually given inside your data sheet, the second page of your exam paper. Now for the equation that you are seeing right over here, where B is equals to mu naught Ni, you don't need to remember this. The syllabus doesn't require you to remember this, but in the event that your questions require you to make use of that, they will give you specifically inside the question itself. Now for the next section, we look at the force on a current carrying conductor or wire. Earlier, we mentioned that when current passes through a wire, it produces its own magnetic field, such that when this wire is placed inside another magnetic field, the wire interacts with it and experiences a magnetic force. This is provided that the wire is not parallel to the field, but at a non-zero angle to the field. If we had wanted to demonstrate this, you could use a copper wire that is held by clamps inside a uniform magnetic field and positioned perpendicular to the field itself. The copper wire that we're talking about is this section of wire here, and is held inside the uniform magnetic field by clamping it at both ends here. Your uniform magnetic field is actually provided by permanent magnets that are attached with opposite poles facing each other to a U-shaped iron frame, so that a strong uniform magnetic field will be created in the space between. What do we mean by that is if you look at your diagram in this direction here, your U-shaped iron frame is something that looks like this. And then you are going to attach two bar magnets at both these ends, such that you have opposite poles facing each other. So when they are arranged in this manner, you will get a uniform magnetic field between the poles of the magnet. And your wire is right in the middle right now. The permanent magnets are placed on the top band balance and the reading is set to 0. Then you close the switch and let current flow so that a magnetic field is produced around the wire. So right now you close the switch, current will flow through your circuit in this manner. So as the current flows, it will cause a magnetic field to be produced around the wire. And that magnetic field of your wire will interact with the magnetic field of the magnets. The interaction between the magnetic fields of the wire and permanent magnets will cause a magnetic force to be exerted on the wire. So say for example, right now the wire has a magnetic force acting downwards on it. This is the magnetic force acting on the wire. According to Newton's third law, the magnet itself should also experience a force. That force will be equal and opposite to the force exerted on the permanent magnets. Because if you recall what you learned under Newton's third law in AS, when two bodies interact, they exert equal and opposite forces on each other. So if right now my magnetic force on the wire is downwards, it follows that the magnetic force on my magnet must be directed upwards. Okay, this in turn will cause a change in the balance reading because the permanent magnets were resting on it in the first place. Since the top band balance reading is actually caused by the magnet resting on top of it, if you have an increase in reading, that means something is actually pushing down on the magnet. The force on the magnet is downwards, and thus, according to Newton's third law, the force on the wire should be upwards. So if you look at the diagram on the left here, when your reading increases, something must be pushing down on the magnet. The force on the magnet must be downwards. And then according to Newton's third law, the force on the wire must be opposite in direction. It must be upwards here in this case. And then conversely, if your reading is decreasing, that means something is actually pulling up on the magnet. The force on the magnet is upwards, and thus the force on the wire must be downwards, according to Newton's third law. If you now look at the other diagram here, your reading decreases, something must be pulling up on the magnet. The force on the magnet is actually upwards, and then according to Newton's third law, the force on the wire must be downwards. So this is how you would predict the direction of the magnetic force based on the top band balance reading. But if you do not have any top band balance reading to work with, is there another way in which you can predict the direction of the magnetic force? You can actually make use of Fleming's left-hand rule. Because the direction of the magnetic force depends on the direction of the magnetic field as well as current direction, all three of them are actually always perpendicular to each other. Under Fleming's left-hand rule, you are supposed to orientate your thumb, your index finger, and your middle finger perpendicular to each other. Your thumb represents the direction of the magnetic force, your index finger represents the direction of your magnetic field, whereas your middle finger represents the direction of your current. For the direction of your magnetic field, it's always from the north pole to south pole of the magnetic field that the wire is in, whereas your current I is following the direction of conventional current. And lastly, your F is the magnetic force acting on the wire. If you apply Fleming's left-hand rule to the example in the previous page, the current in the wire was flowing in this direction, whereas the direction of your magnetic field is from north to south. So if you orientate your fingers of your left hand according to Fleming's left-hand rule, you will notice that your thumb is pointing upwards. This is the direction of the magnetic force acting on the wire. Okay? So now we know that we can use Fleming's left-hand rule to predict the direction of the magnetic force, but what about the magnitude of the magnetic force itself? We can actually find it out from the change in balance reading, but at the same time, we can actually calculate it out from a certain equation, provided we know certain things. For a wire of length L carrying a steady current I situated inside a magnetic field of flux density B, provided that the wire is perpendicular to the field, the magnetic force Fb acting on the wire will be given by Fb equals to BIL. From here, the equation can be rearranged such that B is equals to F over IL, from which the magnetic flux density B, which is measured in Tesla, is defined. Magnetic flux density B is the force acting per unit current in a wire of unit length, which is perpendicular to the field. When they say wire of unit length here, it already means per unit length, okay? And one other thing to note here is that you must include the term perpendicular to the field here, because this equation is for wire that is perpendicular to the field, okay? So this one is talking about the definition of the physical quantity, but what about the definition of the unit, the Tesla here? 1 Tesla is the magnetic flux density normal to a long straight wire carrying a current of 1 amp that produces a force per unit length of 1 Newton per meter. Okay, so here, notice that one of the things that you should also include is that the magnetic flux density must be normal to the long straight wire. Normal here already means perpendicular, because in the first place, it also came from this equation that you have over here. Okay. So notice that when you're defining 1 Tesla here, every other related quantity must be in terms of 1. Since flux density is equals to magnetic force per unit current per unit length, in order to have 1 Tesla, your force must be 1, your current must be 1, your length must be 1. That's why here is current of 1 ampere that produces a force per unit length of 1 Newton per meter. Now, what if your wire is not perpendicular to the field, but rather it is at a certain angle theta to the magnetic field? In the case where the wire is at an angle theta to the magnetic field, then the magnetic force Fb is given by Fb equals to BIL sine theta. Now, why is there a sine theta here in the first place? If you look at the diagram that you have here, if you have a wire that is at an angle theta to the field, this is the direction of your current flow. You can actually resolve the current into 2 perpendicular directions, such that you have one that is parallel to the field, and then another that is perpendicular to the field. So for the current that is perpendicular to the field, because it's adjacent to the angle, this one will be I cos theta. And then for the one that is perpendicular to the field, this one will be I sine theta. Now, the current flow parallel to the field, I cos theta here, does not produce your magnetic force. Whereas it is the current flowing perpendicular to the field that is actually producing your magnetic force. So I sine theta here produces your magnetic force, okay? So right now, if it is the current perpendicular to the field that causes your magnetic force, Fb equals to B times I sine theta times with L, giving you BIL sine theta. That's how you got this equation in the first place. Now from that equation, the force will be maximum when the wire is perpendicular to the field. The angle theta here is 90 degrees. Sine theta will be a maximum, therefore your magnetic force will be a maximum. But on the other hand, your magnetic force will be 0 when the wire is parallel to the field, because in this case here, theta is 0, sine theta will be 0, therefore Fb is 0, okay? And one other thing to note is that when you're talking about the equation for the magnetic force, this L here refers to length, but specifically it is the length of the portion of wire inside the magnetic field. It isn't necessarily the entire length of the wire. What I mean by that, if you just look at the previous page, it is the copper wire right over here. If you had wanted to find out the magnetic force acting on the wire, it would have been Fb equals to BIL, provided that the wire is perpendicular to the magnetic field here. So this L here must be the length of wire in the magnetic field, in the B field. So right now, that L actually refers to this particular length over here. This is the length of the wire inside the magnetic field. It isn't the length of the entire wire over here. We do not use the entire length of this wire. Instead, we use the length of the wire that is inside the magnetic field only. Okay? For the next part, we go through something called current balance before we do the past year questions. A current balance can be used to investigate the force on a current carrying conductor inside a magnetic field. Your current balance actually looks like this. You have a wire frame that is shaped in a particular manner, and then after that, you want to balance it on pivots. Okay, so from here, if you have current I that flows through the wire frame of length L inside the magnetic field of flux density B, you would eventually have a magnetic force FB that pushes the frame downwards. So right now, there's actually current flow coming in like this. So as the current flows through the wire and the wire is inside a magnetic field, you want a magnetic force that acts downwards on the wire right now. So the idea here is that you then want to add weights to the other side of the frame so that the wire frame can be restored to a balanced position. If for the case where you have a magnetic force that is at this position right now and is directed downwards, you're going to have a moment that is in this direction. So you want to counterbalance that moment, you would have to put small weights at the other end here so that you have another opposite moment over here. So if you add just the right weights, the wire frame should be restored to a balanced position. So if you apply the principles of moment here, the moment due to the magnetic force must be equal to the moment due to the restoring weight here. And now, if you were to assume that the pivot is at the middle of the wire, this is how the diagram would look like. Your pivot being over here, your magnetic force FB is acting downwards here, your weight is acting at the other side. They will actually exert opposite moments. The magnetic force will be exerting a clockwise moment, whereas the weight will be exerting a counterclockwise moment. So right now, if the weights are restoring balance to your wire frame, you could say that your clockwise moment is equals to your counterclockwise moment, which is now FB over L over 2 equals to W times L over 2. The perpendicular distance are the same here because your pivot is in the middle of the wire. So this one is L over 2 and this one is L over 2. So they cancel each other off, eventually giving you FB equals to W. And then you already learned just now that the magnetic force acting on a wire perpendicular to the magnetic field is BIL. So this one changes to this. And then you already know that weight is equals to mg. So this changes to this. So from here, you can actually do some calculations to find out specific quantities that are required by the question. Okay. So let's just do some questions from here.